universe is calling you. The universe is calling me. It speaks both day and night. It's full of dark and light.
Hey, welcome everybody to Sky Tour Radio. This is a live show. That's right. It's a beautiful 17th of September 2023. And of course, Daryl's with me. How you doing, Daryl? He's doing fine. He's just muted right now. In any case,
well, you did say it's live radio.
That's right. That's right.
Okay, I'm good, thank you. How are you? Hello,
Good.
everybody.
I'm doing fine. You know, Daryl, tonight I figured, we're going to have some fun because in Sky Tour live stream, we spend a lot of time looking at an interesting phenomena in the universe, and we bring you the universe live in real time. That's what we do. And so one of those things that we talk about a lot, and you and I have spoken of this many times, are these Wolf-Rayet stars, these very, very hot stars that are evolving rapidly and will eventually go supernova. And of course, they're leaving debris behind even before they go supernova. It's just an incredible set of stars. And so we're going to talk a little bit about those. We're also going to talk about the most incredible stars that are really dangerous to be around. In fact, the topic for tonight is dangerous places in the universe. And we're going to talk about some of the most dangerous locations you might ever not want to go. And yeah, I know, right? And among them, besides these Magnetars, are Pulsars and O-type stars. We're also going to talk about, besides the Wolf-Rayet stars, we're going to talk about some other types of locations like black holes. Clearly, no one wants to be near black holes. We'll probably hit those first because black holes are really among the worst offenders, I would say. And there's so many theories about black holes, about, the universe is just one giant black hole. We're inside it. Okay. Now that seems so far-fetched until, and it still is far-fetched to me as an astronomer, but it seems far-fetched. But then again, when you consider that in Messier 87 in the Virgo cluster, this beautiful big elliptical galaxy, and Darryl, of course, knows this, there's a black hole that's multiple times the size of our entire solar system. Now, keep in mind, I think it's like 5 or 6 times the size of our solar system. That's the black hole lurking at the center of this massive galaxy. And that particular black hole kind of being that size is interesting because people always think black holes are this one little tiny, infinitely small point, that is just very, very gravitationally strong. And that's not really true. That's just because our math needs to have a central singular point to reference the force to. So we don't even talk about that. We talk about the diameter of a black hole. It actually has an actual diameter. That diameter goes out to a location at the edge. All right. And that edge is known as, Darryl, you can tell, I'm sure.
The Schwarzschild radius.
The Schwarzschild radius, that's correct. That's the
event horizon.
The event horizon, that's exactly right. That's the definition of the surface, quote unquote, of a black hole. And when we say surface, it's the point where space gets bent so much that if light passes that threshold, it'll just circle around endlessly in there. The light isn't being bent. The light is just following the curve of space because light has no mass. Photons are massless. So that's why light can't escape a black hole, because the light is following the curve of space, and space is curved very steeply in the presence of a black hole. And the closer you get, especially that point called the black hole radius, a black hole event horizon, as Darryl just mentioned, that is the point of no return for everything. But at that interface before that point, that event horizon is leaking all kinds of energy. And so you'd likely be quite dead long before you got to the black hole. You're going to get high intensity radio waves, you're going to get gamma rays bombarding you. And that's something that, I'm sorry, but you were just not built to accept large doses of gamma radiation.
I like spaghetti though.
Yeah, right. And that's the next point. And if we get close enough to a black hole, and we start heading into it, you do like you do when you jump off a very high diving board. You go in feet first, right? You're not going to go in head first. But if you go in feet first, your feet will feel the gravitational pull much stronger than your head at a certain point, because the gravitational gradient gets very steep. So it increases exponentially when you get to a certain point. And by the time you start to cross into that gradient of gravity, your feet are getting pulled more than your head. And so you get stretched out. And the term, as Daryl's alluding to, is called spaghettification. Okay. And, sometimes we like to make up names, right? And I didn't make that name up. But spaghettification is interesting because it's exactly what happens to the human body. Now, in reality, it means we would just be ripped to pieces, right? Your feet would be ripped off, your legs would be just stretched into gelatin, and etc. I mean, it's a nasty way to go, all right? But that's if you could actually make it to the event horizon. In all likelihood, the radiation being given off would probably fry you long before that.
Yeah.
So you'd be a piece of fried chicken being spaghettified. Right?
Black holes, just the name, it scares some people. And if you go back and watch that old Disney movie from the late 70s,
Yeah.
The Black Hole, it was Disney's answer to Star Wars, and it was a dumb movie, but
It was.
black holes are scary, and some say, as you alluded to earlier, our universe might actually be inside a black hole. It's a long story I won't get into now, maybe later, but they just sound scary. But at the same time, folks, a black hole ain't going to come get you. Probably not.
Although, tell the folks about the Hyades story you just told me, because I had seen this, and it has to do with the closest black hole to our solar system.
Yeah. There's a star cluster in Taurus called the Hyades. I'll show it during the deep dive later, if I remember. It's a V-shaped cluster of stars with a red star, Aldebaran, representing, it's the head of the bull in Taurus, the bull, and Aldebaran is its eye. It's the closest star cluster, open cluster to Earth. It's about 150 or 170 light years away, and the Pleiades sit just above it. You've probably seen it whether you know it or not. And there's announcements out just recently that they say they have discovered possibly several black holes in the Hyades star cluster. And this is interesting because, again, it's about 150 or so light years away. And before that, the closest black hole they thought was over 1,000 light years away. So all of a sudden now we've got one like on the order of 10 times closer to us than before, maybe.
And here is the Hyades.
Yep.
Okay, there's an image of it so you can see. And Daryl's talking about Aldebaran, which you see right there.
Yeah. And now Aldebaran doesn't actually belong to the cluster. Aldebaran is only about 70 light years away, I think. So it's a foreground object, but where it sits in front of the Hyades cluster there, you see that wedge shape. The point on the right is the nose of the bull, and Aldebaran is his red eye, and then his horns go off to the left out of frame. It's up late in the evening now, actually, and it's a harbinger of fall and winter to come.
Yeah.
And it's got black holes in it, and they're coming to get you.
Okay. Everything except the "they're coming to get you" part was correct.
Well, like I said, they're scary, so I had to scare people.
No, that's all right. Halloween's coming, so we may do a Halloween show where we talk about some of the more scary objects in the universe. If black holes, of course, will be among them for sure. But it is interesting,
Yeah.
you know. And of course, I got the question a few times. It's inevitable. With our telescope and in the desert that we do sky tour live stream with, will we actually be able to see a black hole? And the answer is no. And I know that's obvious to many people, but well, the answer would not necessarily be no if it was associated with a star near it that could be causing the star to act weirdly. And that's where we're actually going to talk about that tonight. There are these stars called Wolf-Rayet stars, and that's WOLF like the animal, and Rayet, RAYET. And these Wolf-Rayet stars are fascinating, frightening, dangerous places. And you don't want to be anywhere near a Wolf-Rayet star because some of these stars can literally rip you to pieces. And some of the more highly active ones, which we'll talk about first tonight, these guys can destroy you from hundreds of miles away, and they're only the size of Manhattan Island. So this is an amazing set of stars.
Miles.
That's correct.
I would
That's
think
right.
more like a light years.
Well, no, I mean, remember okay. We're going to talk about it. I don't want to give it away, but it has to do with the magnetic field. But I'm going to talk about that.
Very good.
Now, in our most dangerous places game, one of the most dangerous places are these special types of neutron stars. Now, some of you know what a neutron star is. You have a vague idea. And many of you say, well, neutron stars are formed in supernovae, and that's correct. When a supernova explodes, the star used to be there, of course, and it's wiped out. And in the center, if there's anything that survives at all, it can be a neutron star, it could be a pulsar, or it can be another type of neutron star called a magnetar, or it can be a black hole. It depends on the mass. And at certain points, these neutron stars can end up with such a large magnetic field that they are a class all their own. And that class is the class of a magnetar. Now, magnetars are neutron stars. And the way a neutron star really forms is if the star is a certain amount of mass and the supernova explodes and destroys much of the star, you might have on the surface of that remaining core in the instant moments right after the supernova, you're going to have a bunch of protons and electrons all running around. And sometimes the protons and electrons will be forced into each other and cause the creation of a neutron. And if that happens all across the star, which it does, then you end up with mostly neutrons on the surface of this neutron star. And neutrons have their own repulsive force. So if you crush them together, they can resist being crushed further. All right. And that resistance is called neutron degeneracy pressure. Right. And that's a similar analogous force to electron degeneracy pressure, which is the one for not neutron stars, but white dwarfs. White dwarfs are the size of the Earth. And if the star is a certain mass, when it begins to collapse, it can't collapse any further because electrons are crushed together so hard that they push out with their own repulsive force, effectively, resistance. Okay. And that resistance prevents the white dwarf from collapsing further. That's electron degeneracy pressure, pushing outward, holding that star up. In neutron star degeneracy, the neutrons are doing that work. Now, what's interesting is that in a neutron star, normally these neutrons, after a supernova, in the moments after a supernova, literally within in the first 10 seconds, the neutrons are starting to circulate and form these convective cells because, like a pot boiling, because this convection takes place due to the high temperatures and the strange way in which neutron stars operate and the physics that operates on these highly compressed, highly gravitationally charged bodies. And initially, that circulation under high temperature with those convective cells will start bringing stuff to the surface of a neutron star and radiating heat away. Okay. Now, the neutrons actually behave like a fluid at these temperatures. And this also causes something else to happen because along with neutrons, you have a few protons and electrons that are running around. And as you know, moving electrons and protons are charged. Electrons are negatively charged, protons are positively charged. So you have these additional currents and current eddies running around. And if they're following these convection cells and actually doing this work as well, now what you can end up having, and I'm going to get back in focus here. Okay, what you can end up having is a charge generator. And that charge mechanism that generates electrical currents, we call a dynamo. Earth's doing it, and it's generating electrical currents between the solid inner core and the molten outer core moving around it. Now, that dynamo process creates a magnetic field. So these neutron stars do a similar thing, use these convective cells and moving protons and electrons, and they generate lots of electrical energy and lots of magnetic energy, magnetic field. All right. Now, if the neutron star was moving very fast in the beginning, then this convection is very efficient and a lot of that heat gets radiated away. And so the neutron star's magnetic field comes down to something that's a little more normal or even very low. Okay. But if it was not rotating fast to begin with, then it's not as efficient. And so what happens is that magnetic field amplifies over time because the magnetic field is folding over on itself. Okay. And it gets bigger and bigger and bigger. And so we end up with this, again, this fluid of neutrons moving around and protons and electrons. And it's effectively a friction-free location. So it's going to keep on going. And they act like what we call a superfluid. And this allows the motion to be maintained and allows this dynamo to continue. And it creates this massive magnetic field. And I know that that's a kind of a complicated way of describing it. Just think of the fact that a neutron star that's a slow rotating star can actually become a magnetar. And this high magnetic field is extremely dangerous for us because this star, this remainder, is only 12 miles in diameter. Okay, figure the length of Manhattan Island. Okay. Now, the strength of the field is 10 to the 13 to the 10 to the 15 Gauss. Now, what's that mean? It means a 1 with 13 zeros after it or a 1 with 15 zeros after it. That's a huge amount of Gauss's magnetic field measurement. Keep in mind that the sun's magnetic field is about 1 Gauss. Okay, so we're talking about something that's minimally 10,000 trillion times more roughly than our sun's. That's huge. And the thing is, they'll, as I said, Gauss is a measured magnetic field. But imagine what that could do to a body that utilizes iron as we do. Now, it's ferrous, and a ferrous material is subject to magnetic fields, right?
Yep.
We would be torn apart, literally melted at the subatomic level. Now, as an example, that's like saying that if you put one of these 12-mile diameter magnetars over Manhattan Island, you would be melted into nothing if you were anywhere closer than Charlotte, North Carolina in every direction. Okay, now Charlotte's just over 500 miles away. You have to be 100 miles further to be safe. It's about 600 and change miles away from Manhattan at that distance, where that magnetar would melt you down to nothing. So
can I jump in there for a second?
Please do.
This is like a scalar thing, comparison. As Mark says, the sun might have a magnetic field of 1 Gauss. It's about 880,000 miles in diameter, about 110 times the Earth's diameter. And it can do things like the Carrington event that somebody in chat mentioned earlier, that we get solar flares and solar storms. And 1859, it knocked telegraph wires out all over the country. And they had tremendous displays of aurora borealis as far down as the tropics. And if you take a jump to where if you turn the sun into a white dwarf, you take that solar mass and you can press it down to the size of the Earth, from 880,000 miles down to 8,000 miles. Imagine how dense that must be and how much more powerful magnetic fields there would be. And now if you take that and compress that 8,000 miles down to 12 miles in diameter, how dense, how heavy that would be, and how much stronger the 10 to the 13 or 10 to the 15 times Mark mentioned its magnetic field could be. And it's absolutely, this is the stuff nightmares are made of. Luckily, we don't have any very close to us, hopefully.
No, we don't. But keep in mind, that's if you take the sun and shrink it down. The stars that make a magnetar are between 20 and 30 times the mass of the sun.
Yep.
And they get shrunk down to those. I mean, you have to be that big, that massive to compress down to the fact that you have to create neutrons out of the protons and electrons.
Yep.
And so to make that neutron bath, you need to have that compression, and that mass is required for that. But I want to think it was Marcin Johansson in the chat that actually mentioned this about Carrington event. So thank you, Marcin. That was an excellent observation and true. We have a lot of people that are regulars in our Sky Tour live stream here tonight out in the chat. And if you guys have any questions, please feel free, because we're going to do a lot of chat answers tonight too. So that's all up to you. By the way, I wanted to mention Tara Diulis is usually with us. She's off tonight because she's on travel, and she will return for the next Sky Tour live stream. So we wish her well on her travels. I talked to her earlier. So make sure you throw your questions in the chat, and Daryl and I will both be looking for them. So that said, the magnetar then is one of these places that is really, really dangerous. Now, one of the things that happens with magnetars and neutron stars in general is that you have things called star quakes. Star quakes, yeah, like earthquakes. Yes, like earthquakes. But they're on the surface of the star. Now, how can that possibly work? Well, you have to understand that at the compression that these and contraction and compaction that these star cores are left with. Remember, there's no fusion going on anymore. These are just hard shells. It's like if you could touch a neutron star, it would feel like a billiard ball. All right. And a billiard ball that's so hot that long before you could get close to it, you'd be burnt to a cinder if you weren't torn to bits by its gravitational field. And if it was a magnetar, you couldn't get anywhere near it before the magnetic field would just rip all the atoms in your body into their components. In fact, the quarks would be pulled out of the protons, and you would end up with just a slurry of subatomic particles. Boy, it doesn't sound really exciting at all, does it? That sounds like, I don't want to go there ever. I mean, I'd like to see pictures of these things, but boy, oh boy, it's not something that I expect that we'll be able to see anytime soon, So all that said, the magnetar is one of these really, really scary places. And the other thing that magnetars give off due to these star quakes, as I mentioned, are bursts of gamma rays and X-rays. And as you know, there's a rule that you can't have more than a certain number of X-rays from the dentist per year because it's dangerous, all that X-ray radiation. Well, multiply that by 1 million, and that's what an X-ray burst at in close proximity to one of these magnetars would be. So you would literally be disassembled by the X-ray burst. And if that wasn't good enough, and you really wanted to be destroyed in any other ways, well, then you can just wait for the inevitable gamma ray burst as well. So you would literally be dissected by the radiation long before you even got there. So this is what magnetars are. They're neutron stars that are basically on steroids. Okay, so this is an artist rendering of a neutron star. Okay, but a magnetar in particular. And those lines indicate magnetic field lines. No, you wouldn't see it just like that. That's just the lines are simply just to illustrate the lines of the magnetic field, and that's all. Now, as far as the neutron star types, we kind of alluded to this. You have the magnetars on the left there. The magnetars are the high magnetic field ones. You have the pulsar, and these stars were rotating faster than the magnetar class of neutron stars, and therefore their heat could dissipate faster, and the dynamo that creates the magnetic field could shut down sooner, and we didn't have as much of a magnetic field developing around those. But the pulsar has at its poles usually these hot spots of material. These hot spots are like lighthouse beacons. As the thing rotates and rotates and rotates, right, we end up getting, as it rotates, we end up getting this lighthouse beacon flash right by us, and we see that from here. The Crab Nebula pulsar, the Vela pulsar. Okay, there's many pulsars that actually flash us. Now, the Crab Nebula pulsar is that like 30 times per second, I believe, Daryl, for the Crab pulsar.
Yes.
30 or 33. Now imagine a star 12 miles in diameter, the size of Manhattan Island, spinning 30 times per second. Think about that. That's a fast rotator. And so you would think that at anything rotating that speed should tear itself apart. But because neutron stars are so compact and have so much mass and have such a high amount of gravity, the gravity actually holds them together with those rapid spins. And if you think that 30 times per second for a 12-mile object is a lot, it isn't even remotely close to the fastest spinning pulsar and neutron star that we've seen. The fastest is over 715 times per second. Imagine that. A 12-mile diameter object spinning over 700 times per second. Isn't that crazy? But that's exactly what could happen with these neutron stars. And what that shows you is how strong gravity can be. Yet gravity is the weakest force in the universe. But in compact objects, it's very, very strong, right? So that's kind of interesting. Now, you can also have the combination of both of these types of neutron stars. You can have a magnetar and a pulsar together. And the magnetar and pulsar together are a whole nother, there's 6 that are both that we know about, 6 pulsars and magnetars that we know of together. Okay. We know about 3,000 or so pulsars, like in the middle pane there. And the magnetar, oh gosh, it's maybe 1,000 times stronger than the regular neutron star. And it's actually 100 million times more powerful than any magnet we've ever made. All right. So there's only about 30 of these that we've discovered so far. All right. But so we have 3,000 pulsars, 30 magnetars, and only about 6 pulsars and magnetars that we've seen together. So that's pretty much the magnetar world, and it's quite crazy. So that said, I'm pretty sure that we would probably want to stay away from those, And these are, again, the magnetar is among the worst place to be. But what about one of the less worst places to be? Well, we could take a visit to some of the stars in the spectral class O. If we look at this diagram is our famous Hertzsprung-Russell diagram. If you look, okay, this is luminosity, and those numbers, 10 to the third, 10 to the fourth, 10 to the fifth. Okay, that tells you how many times more luminous they are than the sun right here, which is at 1. Okay, and if you go into the middle of the diagram, that's where the sun is. And that snaky line going up top here, that's the line of the hot blue stars. And then all the way down the bottom over there, you can see it goes all the way down to the M stars over in the corner. And that snaky line is called the main sequence. And we've seen that stars actually match this diagram. They actually, their positions are approximated based on their color, which is down the bottom here. And that color is actually, related to temperature. And then their brightness up here. And luminosity is the intrinsic brightness. It's the brightness that a star would have if you could compare them all at the same distance, and say that's our standard. And that's kind of what this is. It's sort of a base standard. All right.
Can I jump in for a sec?
Yep.
The main sequence is where stars are burning hydrogen, where they're undergoing hydrogen fusion. And this is called the Hertzsprung-Russell diagram. Carry on.
Okay, yeah. And the Hertzsprung-Russell diagram, or the HR diagram, as we've always called it, as Daryl said, yes, the main sequence is where stars convert hydrogen into helium in their cores. And if they're massive enough, like the stars up here in the top, then they can convert helium into carbon after that. And then they can take carbon and make it into nitrogen and oxygen isotopes. An isotope is just a different form of the same atom. And go all the way to about iron for the most massive stars. Iron is number 26 in our periodic table. And you'll know that there's a whole number beyond that. So where do those elements come from? Well, in the massive pressures of a supernova explosion, some of those are made. But a number of them are made in other ways. And stars like the sun can make other elements in the periodic table slowly. That's called the slow process. And so, and it has to do with neutron capture, it's called, when a neutron ends up in an atomic nucleus or in the nucleus of an atom, it can get converted to a proton under certain conditions. And we call an element the next element when it has a new proton in it. So you have a carbon atom, okay, and you add add a proton to it, and it becomes a nitrogen atom, right? And so that's what happens with stars. They can do that. But by and large, supernovae create these colliding black holes, create more elements, merging neutron stars, like we've been talking about, like magnetars and pulsars plus magnetars. Okay, colliding neutron stars actually can generate gold. Gold, actually, most of the gold in the universe comes from these mergers of neutron stars. In the resulting, annihilation that occurs. And so it's so fascinating to see just what's created in the universe and how everything that makes you up came to be. And that's kind of cool, So this Hertzsprung-Russell diagram, that's kind of our standard. And if you look at the top here, you'll see right up at the top, okay, you compare down the bottom here, it says O, and then it says B, okay? Those are our spectral classes, O, B, A, F, G, K, M. They go from hottest to coolest, and in many cases, largest to smallest, okay? And for the main sequence, or the hydrogen-burning stars, as Daryl was pointing out, these are the most massive to the least massive, okay? And so these massive O stars at the top here, you can have stars that are 60 times the mass of our sun, 50 times the mass of our sun, 30 times the mass of our sun. It's amazing and difficult to actually believe just how big these stars can be until you actually see them through analysis and discovery in astronomy. So that said, it's these O stars up here that we're going to be talking about next. because it's those giants, those biggies up there that live the shortest amount of lives of time. The brightest and bluest of them are the shortest lived, which I think is kind of interesting, right? So O-type stars also power a lot of these nebula that we see in Sky Tour live stream. Among the nebula, we have nebulas like this one. Okay, this is the Lagoon Nebula at the right down there. You can see it, and it's being powered by an O-type star. You'll notice the brightest section of this nebula. That is where this O-type star is. Now, O-type stars live maybe 3 million years. Okay, but they're very, very luminous. They're extremely bright. Many of the stars in Orion are O-type stars, and they're classified by their temperature and the spectral lines that we see when we disassemble the light coming from them. And the temperatures can be anywhere from 30,000 Kelvin, which is 53,500 degrees Fahrenheit, all the way to 93,000 Fahrenheit, which is 52,000 Kelvin, right? And, these are very, very hot stars.
Our sun, by comparison, is what is it, 5,000 Kelvin or 6,000 Kelvin, which works out to maybe 10,000 Fahrenheit.
Yeah, you got it, 10,000 Fahrenheit. Yeah. So when you think about it, the brightness of a star that hot is going to be larger too, because the luminosity or the intrinsic brightness depends on a number of things. It depends on the temperature, and it depends on the radius. And usually these stars are big and hot. So the brightest, highest luminosities will be from these O-type stars. And the luminosity is generally between 100,000 and 1,000,000 times that of the sun. Now, think about this. You can't look at the sun for very long, can you? Right? And you can stay out in the sun for an hour without, anything on, and maybe you get a little bit of a minor redness and burning. But the stellar exposure to just one fraction of a second to one of these O-type stars is fatal. And not only that, you probably wouldn't even feel it. It would be like an instantaneous vaporization of your body. So the O-type stars are really quite inhospitable. Not only that, in most cases that we've seen, in fact, all cases that we've seen, there are no O-type stars that have planets around them. And the reason is because they have pretty high stellar winds. These stellar winds will literally rip the skin off of your body, okay? And it's the radiation. So, they've shown movies where high radiation hits somebody. Like remember Raiders of the Lost Ark, the first one, where the German guy goes, "It's beautiful." He's got the little round glasses, the German guy. And then of course, and he melts, right? Well, imagine much faster than that. So fast that he can't even say it's beautiful. He can't even say it's, So that's the kind of thing you'd see with the luminosity that approaches something like an O-type star. And because of that stellar radiation and because of that radiation pressure, most of the dust and gas around the O-type stars is dispersed. And the O-type stars also aren't around long enough to allow planets to form. They mostly live between 3 and 4 million years, as opposed to our sun, which is 5 billion to 10 billion years. Actually, we're about 4.5 billion years into our existence with the sun, and it can go to about 10 billion years. And that seems like a long time. But then at the end of this diagram right here, okay, down here at the bottom right, those M-type stars way down there on the right, those stars can live literally over 1 trillion years old. In fact, there are no M-type stars in our universe that have died yet from the beginning of time, from the beginning of the universe. Not a single star that's an M-class, M-type star has ever died. They're still all in existence. And they're the most plentiful star in the universe, and they have the most planets around them of any other type of star in the universe. So you see, the universe provides platforms for life, and O stars are not it. Okay, they are just not it. An O star powers this nebula too. This is called a Trifid Nebula, or the Trifid, as some will call it. Actually imaged this the other night when I was just testing our system. And this is down in the constellation of Sagittarius. That red thing is an emission nebula. The dark lines in there are dark dust lanes that are between us and the nebula behind it. They're actually silhouetted by the nebula. Then you have that blue stuff around it, and that's actually scattered light called a reflection nebula from the dust that this is all embedded in. But there's also a lot of gas there, and the O stars are ionizing the hydrogen gas, causing it to glow red. All right. So O stars are really powerhouses. They live a short amount of time. We know that there have been trillions of O stars that have come through the universe. They've come through. They've were born and died, leaving behind lots and lots of dust and gas, filling the universe and the interstellar medium with all kinds of new elements. And then when stars that come along later are made, they're made with those elements. So in their outer atmospheres around these stars, within these stars, you have the core, mostly hydrogen, right? And then around that, you have all of this material that is not doing anything except existing. It's plasma, and it's not responsible for the heat you feel from the star. All that's coming from the very core of the star, which is a much, much smaller little walnut in the middle of this gigantic object. So I think, if I recall, and Daryl, maybe you know this, if we consider our sun, the core in the sun might be the size of Jupiter or a little less. I can't remember. Do you remember that analogy? There was one out there.
Not offhand, no.
Okay.
Sorry. I'd like to add, though, to what you're saying about the O stars and the nebulas. I think it's sad that when we look at those really beautiful nebulas like this, that they're dead because of those O stars. I mean, the O stars aren't going to let anything live in the neighborhood, with possible exception of where we see the little dark tendrils and the dark little globules and globules and Herbig-Haro objects, maybe, which is where new stars could be being born.
Yeah.
But the prettiest things we see in the sky are dead. And you have to get out in the suburbs where we live, out where it's dull and boring, right in the middle of that Hertzsprung-Russell diagram. And then farther down toward the red end, it may be dull, but it's safer out there.
Yeah, in fact, what Daryl's alluding to is what I think is a good point to mention. If you look down the bottom here, you see it says OB and then A. Okay, from A onward, that's the doldrums of our galaxy. Many of the stars that are in the doldrums of our galaxy are in that particular spectral class down there. All right. Now, the luminosity and the color temperature, the OBAFG, etc., together, that makes a spectral type. So the luminosity class is the vertical bar. The spectral class is the horizontal bar. And together, they make the spectral type of a star.
So where we live on that chart, if you read down the left side to where it says 1 luminosity, 1 solar unit, and you go over to the right to where we hit that line, we live on a G. Our sun is a G-class star.
Yes.
And that's right where we are. And it's deliciously dull.
It's deliciously dull. Yeah. That green line you see sort of at that one level here across from this, that line, that green line points to our sun. All right. And so a green line of one, or sorry, that one means that our sun lives there. That's where everything is that we can live on. And it's and this whole snaky line has a Roman numeral associated with it, and that's the V, Roman numeral 5. Yeah. And they're called dwarfs. All right.
When we look at this chart, Where all the interesting and dangerous stuff happens is up toward the upper left and then
Mhm.
over to the top right. That's where all the scary things start happening, is up there.
Agreed. Yeah,
The magnetars, the black holes, the neutron stars,
that's right.
all that's happening up there at the top left to the top right.
Yep. And the thing is, if we look at this side right here, the white dwarfs right there, that's the end state for stars that are anywhere from A, late B to A down to FGKM. Okay, that are smaller. Okay, from the main sequence, they can actually go from the main sequence through an evolutionary pattern. It takes them down to the white dwarf stage. But if they're really massive, then they're going to end up going into becoming supergiants up there. All right. And those will probably explode in supernovae. All
Yep.
right. And that will lead to these things we talked about here, the neutron stars of various kinds, and so on. And this is just incredible. So we
Can you go
have these.
to the
Go ahead.
diagram for a second?
Yeah.
You see right up at the very top right, those two big red stars, Betelgeuse
Yes.
and
Yeah,
Antares.
right there.
We've talked about them before. They're the two likely supernova candidates in our part of the galaxy.
Yeah, and you know what? Let's mention something about Betelgeuse for a moment. Okay, now we talk about the fact that these always end in supernovae, and it's true. Betelgeuse is interesting because Betelgeuse is the upper left star in Orion, right? So when you look at Orion, you have on the upper left, you have Orion's constellation. You have Betelgeuse at the top left, okay, and then to its right, you have Bellatrix. Down at the bottom right, you have Rigel. Over at the lower left, you have Saiph, Saiph. And then you have the belt of three. 1, 2, 3. And those three stars are all O stars. They're very, very young and they're very, very powerful. Now, the first one in the belt is called Alnitak. And Alnitak, being an O type star, it's under 4 million years old. And I've mentioned this before when Lucy, Australopithecus afarensis, 4.2 million years ago, was walking around, our precursor, okay, was walking around, had Lucy looked up in the sky and had an inkling of anything and said, "Oh, look at that interesting thing in the sky," she would have seen Orion. And it's possible, and very likely, in fact, that Betelgeuse wasn't red. In fact, Betelgeuse was probably one of these hot blue stars. It was an O type star. And then as it used up its hydrogen, it left this main sequence and migrated into the red supergiant phase. We've talked about stellar evolution before, but Betelgeuse was probably, in all likelihood, a very bright, hot O type star earlier. All right. And that means that these classifications down here are based on temperature, all right, and luminosity. So when we see a temperature that is low, like a big red supergiant has, that's only low because the atmosphere of the giant, that the star, is extended so far from the center of this star where all the energy generation is going on that it cools off way out there. So all the stuff way out here, this stuff doesn't even, it doesn't feel as much radiation from the center of the core. So it cools off. It goes from potentially, 90,000 degrees down to 3,000 or 5,000 degrees. Okay. So that's Fahrenheit. So when we talk about the color, you have to remember that color is related to temperature. All right. And so that's why Betelgeuse was probably a hot blue star. And then when it expanded in size, it cooled off and turned red. And then we classify it as this red supergiant. Its outer material is very cool. However, its core is still very, very, very hot and massive. All right, but it's so far away that that heat doesn't get all the way out there. Okay, now Betelgeuse is about 700 million miles across, compared to the sun, about 870,000, as Daryl had said earlier. All right, now it has a surface temperature of around 5,800. All right, and our sun's about 10,000. All right, again, because it's so far from the core. Betelgeuse right now is about 10 million years old. And it left that main sequence, okay, that we talk about here, that beautiful stripe going down the middle here. It left that stripe many years ago. But when Lucy, 4 million years ago, was around, Betelgeuse was a bright blue star. So it hadn't left the main sequence by then, in all likelihood. And interestingly enough, when you look at the belt of Orion today, you see 1, 2, 3 stars. When Lucy looked up at those at the belt, she probably only saw 2, because Alnitak, the leftmost star in the belt, probably wasn't born yet. Because Alnitak's about 4 million years old, and Lucy's older than Alnitak. So it might have been that it didn't even exist yet. Orion as we know it would not look like Orion as we know it back then. Isn't that cool? That's pretty cool. You know, Daryl, if you want to add anything, this is a good time. If you get off mute.
Sorry, I was muted again. Yes, please. Put the HR diagram up one more time. Okay. If you look there at Betelgeuse and Antares up at the top right, you'll see that they going straight down, they are M-class stars, just like those red dwarfs are at the bottom right. What do they have in common? They're both cool red stars. The only difference is that the red dwarfs at the bottom right, those are smaller than the sun. They are intrinsically low mass stars, and they will live a very long time.
A trillion years.
While Betelgeuse and Antares, they're also cool red stars, but they are great big whoppers of stars. And they are prime supernova candidates in our part of the galaxy.
That's right. That's right. Yeah. So that's actually pretty interesting. I mean, I really think it's really important to understand too that this diagram really gives us a huge understanding in one diagram. So when Henry Norris Russell and Ejnar Hertzsprung came up with this diagram, it really was a labor of understanding of the entire universe around us. And you know what? They've tried over time, people have tried to poke holes in what this all means. And it hasn't been able to be disassembled and said, oh, well, that's not right. And that's not right. No, this matches to this day everything we've ever seen. And I think it was created in the 1920s.
Yeah.
So it's actually a very, very excellent diagram. Now, there are what are called evolutionary tracks that you can put in there. So for those hot blue stars up here, you can see there's tracks that are named after people like the Hayashi track and so forth. The helium flash, there's the asymptotic giant branch, all these additional stages of the evolution of a star. And these kinds of things, horizontal branch. So there's all kinds of additional complications to how this all works. And we're not gonna get into that tonight for sure. But it is important to understand this diagram. And this diagram is by far the best introduction if you want to learn about astronomy, because everything you need is on this diagram. How bright is it? What color is it? What temperature is it? There you go. And depending on its position, it gives you some hints as to its radius as well. And that's really important to understand too. You know, so that said, I think that we've talked about the O-type stars quite a bit, and I think that we can leave them to the dustbin of Sky Tour Radio for the moment. But if anybody has any questions, feel free to ask. I'm going to just review in case there is anything like that. Yeah, and we had Kathy describing Lucy to folks out there, which is great.
Yeah, we have about 2 minutes to break.
I realize, yeah. And then let's see if anyone else has any questions while we're here. And if not, that's fine. If you have a question, just put it in all caps so we catch it as we scroll. All right. So that said, all right, good. There's some more in here, but I'm unable to get to them right now. I let them scroll too far. When we come back from our break, we're going to actually talk about the other incredibly frightening places to be and deadly, dangerous places in the universe. Now, let's talk about something. You guys remember the Titan disaster, right? The submarine that went down to the Titanic. The Titan was a carbon fiber cylinder with titanium end caps. Now, I've done a lot of work in oceanography and astronomy. Around here, not so much, but inner space, outer space, that's my bag. Mostly outer space. But the fact that it's really important to understand is that the deep pressure in the ocean is actually far more unforgiving than the vacuum of space. You can actually survive a momentary exposure to the vacuum of space, all right? But you can't survive a millisecond of exposure to the ocean depths near the depths of the Titanic. Isn't that incredible? Outer space actually more forgiving? Well, in both places, you'll die if you're left there for a fraction of a second longer, right? Obviously, in the ocean, guaranteed, but in space, not guaranteed. There was actually some experiments done where somebody was in a vacuum chamber, accidentally exposed to a vacuum. Now, the blood boils the surface of the skin. Boiling is a pressure thing, not a temperature thing. It's another whole science lesson we'll get to at some point.
Mark, can you hold that thought? It's break time.
Yeah, it is. That's okay. All right. Well, we will be back then right after these words.
Hey members, the new KGRA DB app is now available on iOS and Android devices. Gain on-demand access to any KGRA DB programming. Download any show directly to your mobile device to listen or watch on the go. Go to the App Store and search KGRA DB.
Did you know 75% of Americans are chronically dehydrated? If you struggle with focus, run low on energy, or when it's time to finally sleep, you simply can't, this can all be linked to dehydration, and Fuel Up has the answer. Our proprietary formula contains the finest cellular hydration with the strongest immune-enhancing natural ingredients. The Fuel Up system is made up of 3 different incredibly tasting varieties. Wake kickstarts your day with a jolt of caffeine. Play boosts focus while hydrating your cells. Rest not only helps you relax, but also rejuvenates your cells while you sleep. Here's what our clients have to say.
I really don't miss my coffee, and you can tell the difference.
So I'm going to take it for the energy. I'm going to take it for the play. I'm going to take it, all day.
And it works. That's the thing. It works. We love it.
Take the Fuel Up Challenge now, where we offer a Feel the Difference money-back guarantee. Fuel Up for life.
As UFO reports come in from around the world, the Mutual UFO Network, MUFON, is there. We continue to explore new cases and build our massive database. We share our information with the world in a number of ways. If you'd like to be part of our investigative team, you are always welcome. What could be more exciting than exploring the UFO question firsthand? Join MUFON, find your friends.
You're listening to the KGRA Digital Broadcasting Network. We provide unparalleled coverage of trending news in the world of ufology, cryptozoology, and paranormal phenomenon. Whether you're watching our video live stream or listening to one of our audio programs, you are getting the best from world-renowned researchers and hosts, guiding you through topics the mainstream won't touch. Miss one of your favorite programs? no problem. Head over to the members area at kgradb.com for access to our massive library of award-winning content. Make contact, stay connected. Only at kgradb.com.
And we are back. So we're talking about pressure in the deep ocean versus the vacuum of space. And it's interesting to note that when you talk about the deep ocean versus vacuum of space, that somehow the vacuum of space is a little bit more hospitable, as inhospitable as it is. Now, both will kill you, yes, as I mentioned. But in space, you could actually suffer a few seconds of vacuum, and you could possibly survive it. But in the deep ocean, the weight of the mass of that water over your head will literally destroy you, crush you out of existence effectively, and you would not be able to survive that. So either way, you're gonna be like nixed from the planet if that happens. But in terms of, so one of my point was with that was that outer space, it's all inhospitable, but in terms of survivability, it's got a slightly higher survivability of empty space than the deep ocean, which leads to a whole nother thing which talks about habitability of a planet, which is another show altogether. But our planet is habitable, right? But it's not super habitable. A super habitable planet is one where we can survive unencumbered for a full natural life without any dangers. Well, we have weather danger. We have tectonic danger, volcanoes, earthquakes. We have seasons, cold and extremes of heat and cold. And we have places on Earth you don't want to go, like the methane pits. There's a methane pit in Africa called the Gates of Hell. And it was a natural methane seep coming out of the ground, and they lit it on fire to keep the methane at bay. And it's been burning for, 100 years or more? I forget how long it's been. I think it was lit in the 50s or 60s. I could be wrong, though. But it was actually interesting place. I'd like to go there because it's like looking into the mouth of a volcano, but it's methane gas burning. All right. So as terms of habitability, our planet is habitable and we're surviving in spite of it. Okay. Ultraviolet radiation from the sun can kill you. And many people die from cancers generated by ultraviolet radiation, right? And ultraviolet radiation is something that mutates our DNA and causes changes, even from our rather somewhat quiescent sun. So when we talked about O stars and we talked about neutron stars, they're very hot, and the radiation that they give off is mostly in the ultraviolet, all right? And so not so much in the visible, and the visible light of being like 1,000,000 times more luminous for an O star, there's even more ultraviolet being given off. So that's why we talk about these locations as being so inhospitable. You could shield yourself from the rays of a bright star like that, but the ultraviolet radiation could still get to you, and that's the problem. And that's something that we can't shield ourselves against generally. We can stay within our ship inside of a protected capsule and maybe be okay, but it would be baked by the temperatures. So we would have a lot of trouble going to a very bright star in general, right? So speaking of these very bright stars, the next inhospitable, dangerous place is anywhere that there's these Wolf-Rayet stars. Now, as late as 1867, Charles Wolf and George Rayet discovered that there were these stars near the end of their lives that were many times the mass of our sun. Okay. And these stars were extremely bright compared to our sun, up to, no surprise, 1,000,000 times the brightness of our sun, the luminosity. Okay. And 150 times the mass, at least, of our sun. And coupled with that were these very high temperatures, right? You had stars, our star, 10,000 degrees Fahrenheit at the surface. That's nice. How about a star 355,000 degrees Fahrenheit at the surface? That's the upper level of a Wolf-Rayet star, and 1,000,000 times the luminosity is kind of average. There's more and there's less, but I don't know these stars. And Daryl, you know, we've looked many times at these Wolf-Rayet stars within the live stream.
Yep.
And we've seen some really amazing sights as to what they can do and how they act. All right. And, you know, some of them, okay, like here's one. Okay. This is called the Dolphin Head Nebula. And you'll notice right in the middle of that green is that one star, not near the bottom, but kind of near the center. Well, that right there is a very hot star. It's the one of these Wolf-Rayet stars. And the Wolf-Rayet star, these are very well known because of a few characteristics they have that are really, really interesting. For instance, they have extremely powerful stellar winds that leave the star and are so powerful that they literally push the outer layers of the star off away from the core. All right. And that's simplifying it, but that's in effect what's happening. And this pushing effect makes this nebula appear around the star. And then the star being so hot, as we mentioned, anywhere from 355,000 Fahrenheit on down to just like 90,000 Fahrenheit or so, that will ionize any gases that were in any atoms or any mostly atomic nuclei at that point out in the outer reaches. And the atomic nuclei could be things like oxygen. You know, oxygen is the third most abundant element in the entire universe. So it stands to reason that stars that are made with material like this from the interstellar medium are going to be made with oxygen and hydrogen. So you're going to get a lot of these greenish nebulae because ionized oxygen is green, like you see here. All right. And there's also ionized hydrogen, which goes with it. So sometimes you'll see red, sometimes you'll see green. But hydrogen is a much more light nucleus, and it can be pushed away farther and faster than the oxygen by a little bit. So you might see that the hydrogen is on the outside fringe rather than on the inside, because it will make it further out over time than the oxygen. It's just a matter of mass being pushed by the stellar winds we're talking about. You know, now this nebula is reaching out light years. The ionizing prospects of a star like this are so high that it can ionize the region around it for many light years. And so you see, and as Daryl mentioned earlier, he mentioned you're not going to find anything that's life-bearing within several light years of a star like this. In fact, that distance is more like 10 to 20 light years. And if something does take hold, it will have taken hold before the star drifted into its neighborhood, because all these stars are orbiting the galaxy. And the star that's closest to us right now is Alpha Centauri. Well, there's another one, okay, called Barnard's star. And Barnard's star is also moving through. That's a little red star. It's one of these little, I think it's one of the red dwarfs, or it's a supergiant. I can't remember which one it is.
Red dwarf.
Yeah, I thought so. The Garnet star is a red supergiant. Yeah. So Barnard star is drifting closer to us, and it's going to get a little bit closer to us, but won't get as close as Alpha Centauri. But Alpha Centauri is going to drift away over time, and it won't be the closest star to us in the future. However, projections show that there are no stars that will put us in danger that are going to come close to us in the next, several 100 million years. So in that amount of time, we'll either have wiped ourselves off this little rock, or we will have found our way out into the universe. I suspect in the latter, we will find our way out. All right. So again, this is the Dolphin Head Nebula. We took this with SkyTrail Livestream, and it's an example of a Wolf-Rayet star that has used its powerful stellar winds to blow off its outer layers, and you can see that. Now, you'll also notice it's not just a round sphere of material leaving the stellar corpse or the star in the middle. Now, the other thing about these stars is their stellar winds are extremely powerful. They push off all this material, but they're going to go supernova. That's the eventuality for a Wolf-Rayet star, at least as we understand them now. And they have very intense radiation, including X-rays and gamma rays that they give off. And Daryl mentioned it before, no planet could possibly survive this, and he's right. But they create this nebula, and their stellar winds are like 3,000 kilometers per second, all right, pushing outward. That's huge for a star. That's massive for a star. And this stellar wind could eventually reach planets in the outer reaches, planets that might be around other stars, and they'll cause significant damage and could sterilize any burgeoning life on such a planet. All right. So that's a fascinating object. Another one that shows a similar look is this one that we've imaged. This one, known as Thor's helmet, also has a little bit of hydrogen in it. You can see that red little line. And I find it interesting, Daryl, because we've seen in the planetary nebulae, like the dumbbell, we see some harsh red lines that you like to talk about.
Oh, yeah.
And we see it here as well. So we're seeing the oxygen ionized by the star that you can't really see in this image, but it's in there. We can see it. It's just barely visible. And it's a Wolf-Rayet star that's extremely powerful. And the other thing is that, these stars, again, they literally blow bubbles around themselves using their stellar winds, right? Another one that we've seen, this is the Bubble Nebula, saying it blows a bubble. The star blowing this bubble, look, it's almost perfectly round. However, what's interesting is the star doing it is kind of in the top of that round bubble in the overexposed area. And it looks like this because of the nature of the three-dimensional universe and the way in which the material being blown off the star, is actually moving out into the interstellar medium and colliding with other material out there. So that the collision with other material out there is why it has the shape that it has, and why it looks this way. Lubo in China, one of our longtime listeners, says, what other ionized gases are there that we can observe? And he says a part of H alpha, H beta, oxygen 3, and sulfur, I think he means 2. I heard about mercury sodium trail. Well, there are other ionized gases that we see, but keep in mind, hydrogen is the most plentiful element in the universe. Helium is second, and oxygen is third. All right. And we'll see mostly hydrogen and mostly oxygen. So we'll see red and we'll see green. Excellent question, Luo. But, there's going to be helium, right? There's going to be neon. There's going to be other elements, calcium. We'll see in there. And so we'll see a lot of other elements, and virtually most of the elements in the periodic table can show us some type of indication in a star's spectrum when we look.
Yes. I don't have the website in front of me, but there's websites out there that shows the emission spectra for all the elements, basically. And we, as Mark said, we see neon sometimes in the Dumbbell Nebula, for instance. Some of the red is from neon. All elements, I guess, have an emission spectrum. That is, they give off a characteristic color of light when stimulated by sufficient radiation. They also have absorption spectra, which are the dark lines you see in spectra. That's where the elements are between us and the bright object, like the sun.
Yeah.
And so we see the dark lines instead of the bright lines.
Yeah. Now, Lubo mentioned sodium. When you see sodium, sodium has an emission spectrum as well, and the emission spectrum of sodium is yellow. Okay. Now, Daryl mentioned neon as a reddish emission, and it is. However, another gas that can do this is strontium. Strontium makes a very bright red line, a scarlet red line. And I've burned strontium in a Bunsen burner and seen this beautiful red. I've burned copper and seen green. Okay, but it's oxygen that we look at in the interstellar medium most of the time. So there's a lot of iron actually burns yellow as well. But it depends on the temperature that it's being exposed with, and how much what the density of the gases that's actually being ionized. So if you have mostly oxygen mixed with hydrogen, the nebula color is probably going to look green. But if you have mostly hydrogen with just a little bit of oxygen, you're probably going to get mostly red, like we see here. All right. So that's why for Wolf-Rayet stars, we can see both these green nebulae and these reddish nebulae associated with the same type of star. They all have powerful stellar winds. They all have extremely high temperatures. But depending on the predominance of the elements in the star to begin with, when we start seeing the star's stellar winds blowing this material away and separating the outer layers of the star from the core like this, it depends on what the star actually has in it and what's around it in the interstellar medium. Now, what we're seeing here, for instance, in the bubble nebula right here, we're seeing a nebula of hydrogen gas that this nebula sits within. And this nebula is being ionized by that Wolf-Rayet star in part. And so it's showing up as an ionized red, because hydrogen gas, when ionized, looks red like this. And we're also seeing there's probably some oxygen in here, but it's overwhelmed by the ionization. And to Lubo's question, if we look at a complete spectrum of this, we'll see lots of peaks and valleys, lots of peaks, which indicate different elements, okay, or the same element, in different series, okay, of emission. So we'll see lots of different lines in a true spectrum, and we only see visually just a couple, like in here and like in here, But
per Lubo's question, yes, Mercury has a sodium trail. If you ever took chemistry in school, or Mark mentioned putting an element in a Bunsen burner, you may have in school put salt in a Bunsen burner, and it burns with a very characteristic yellow color. If you've ever seen images of telescopes with yellow lasers coming out of them, the European Southern Observatory is a very large telescope, for instance, uses sodium lasers as artificial guide stars. They project a laser up in the sky, and they kind of monitor the sky conditions, how still or how turbulent the air is. They're doing that with with the sodium laser, and it's that exact same sodium yellow color. And Mercury does it also. Jupiter's moon Io puts out a sodium. There's a sodium belt around Jupiter that comes from Io and all the volcanoes on it. Mercury looks really cool. If you take an image after sunset or before sunrise, wherever Mercury is in the sky, and you have a sodium filter on your telescope, you can actually catch the sodium tail coming from Mercury, and it makes Mercury look like a comet, sort of.
That's
has
cool.
a tail.
Well, we have to get to your deep dive too, because I want to hear from you about what's in the sky coming up as well. But I just want to mention again, I want to thank you guys. If you have a question in the chat, Lubo did a good job. He put the word question. And so if I scroll down and I see the word question, I'll know you're asking a question. So please feel free. But Daryl, why don't you get your deep dive ready? And while you're doing that, I'll mention that we're going to talk about some additional Wolf-Rayet stars afterwards and
Okay.
get to as many as we can. But I'm looking really forward to seeing the deep dive.
Very good. Here we go.
All right.
Okay.
So
now this is just before sunset tonight. We're looking west, usually where I start. And here's north over here on the right, and south to the left. And as ever, it might, as this presentation kind of distorts things. The green line is called the meridian. That is the line that runs from north to south that passes directly overhead through the zenith, okay? The red line is the ecliptic plane. That is the plane that the sun moves across the sky over the course of a year from point of view on Earth. And the planets, you see, here's Mercury. They also follow this line pretty closely. It's the plane where eclipses happen, and that's where they call it the plane of the ecliptic. Just to give you a little, quite set yet. It's 6:30. Let's give it a little more time. We'll make the sunset here, and I'm gonna put the atmosphere back for a moment, so it's still bright outside. And Comet Nishimura is right here. Nishimura just moved from the morning to the evening sky today, I believe. And so Nishimura is now in the evening sky. The problem is it is so close. It's a little closer than the planet Mercury to the sun right now, but there's not much angular separation between the sun and the comet. So the sun just set, and hey, you can't see Comet Nishimura at all. You're probably not going to be able to see Comet Nishimura with a naked eye unless you have a dead flat western horizon now. If you go out with a camera, you may be able to catch a picture of it. Dusk gets a little deeper. Okay, so 7:30, and here you see how close it is now. By the time it's getting dark, it's just barely above the western horizon. So, and it's going to vanish in just a few days. It's going to move to the left and down some. It's going to disappear over here, and we'll probably never get to see it. But good luck to you if you try. Okay, so now I turned off the sun, and here's the sky in the west at sunset. Mars is still fighting to keep up with us. Mars is losing the race, though, but it has kept up with us so far. And here's the moon, just a little farther to the left of Mars, or to the southwest. And you'll see the bright star Arcturus, fourth brightest star in the sky. It is getting lower in the west after sunset. Arcturus is the first bright star you see in the springtime, actually. Constellation Bootes, the herdsman. It's the fourth brightest star in the sky. And if you cut up across Corona Borealis and Hercules, then the next brightest star is Vega in Lyra, where my pointer is. Vega is just a hair dimmer than Arcturus. So Vega is the fifth brightest, but to the eye, they look about the same, or Vega might actually look a hair brighter just because it's bluer. Vega is the middle and bright star. It's kind of a white with maybe just a touch of blue to it. Arcturus is a red giant star. It's actually it's farther away, but it is intrinsically a much brighter star. So from there, Virgo is setting also, and here comes Libra, here comes Scorpius. And then we see a thing I talked about on the stream the other night. If you go out and look the same time, maybe, during dusk, about the same time every night after sunset, this time of year, Scorpius appears to kind of hover in the southwest. It'll be in about the same place for a while. I've said in the past that Scorpius, being the southernmost of the ecliptic constellations, the zodiacal constellations, Scorpius comes and goes really fast. But this time of year, Scorpius seems to kind of hover in the southwest. This is a combination of things, mostly that because we're approaching the equinox and the sun is setting earlier every night, well, if you go out, say, 45 minutes after sunset each night, you're kind of freeze framing Scorpius because we're seeing it actually a little earlier in the same place each night. It really is moving, and it's going to go away before you know it. But for the time being, if you go out after sunset and you look in the southwest, you can still see Antares, the Scorpion's heart, and Dashuba there is his forehead. You'll see these two stars, and then you'll see the two stars that make the stinger in the Scorpion's tail, also known as the cat's eyes, Shala and Lasaph. They are here's the tail of the Scorpion, and that's his stinger right there.
Hey, Daryl.
There, here comes the teapot. Yes, sir.
Yeah, I was going to say.
Yes.
You mentioned something else the other day during a SkyTour live stream about how Antares appears to hang for an inordinate amount of time in the sky before it seems to set. Did you mention that? I don't think you mentioned that now.
Yes.
So once you go through that, that's actually.
I thought I just did.
Oh, did you say that?
I thought I just did. Yes.
All right.
It's because we are approaching the equinox here next weekend. This is the last weekend of summer, by the way. A week from today, we'll be in fall, in autumn. But because the sun is moving south as it heads into autumn and toward winter, the sun is moving this way day by day across the sky. Because we're approaching the equinox, the sun is setting earlier every night, and it sort of does a freeze frame thing where Scorpius and Antares appears to hang in the southwestern sky this time of year. And it sort of sits there for several weeks at a time. Pardon me just a second. Okay, anyway, say goodbye to Scorpius pretty soon. Sorry. Here's the teapot in Sagittarius, one of my favorites. There is the pipe nebula right there. If you draw a line from the tip of the spout of the teapot to the bowl of the pipe, right about in between them, right about there, is where the center of our galaxy is. And Sagittarius A star, the supermassive black hole in the center of our galaxy.
Can you zoom in on that
That's
a little?
the easy way to find it. Yes.
There you go.
Okay, you see the pipe nebula right here? It looks like a smoker's pipe. And then Al-Nasl is the tip of the spout of the teapot. You draw a line right there, and the center of the galaxy is right about there. And that's where Sagittarius A star, supermassive black hole, is. Okay, and lots of interesting things are happening there. Let me get back here. Whoops. And the ancients, they saw a half man, half horse shooting a bow and arrow, Sagittarius, the archer. We see a teapot nowadays, okay? There's Al-Nasl, there's Caus Borealis, Caus Media, Caus Australis. Those are the arrow, and Al-Nasl is the tip of the arrow. Those are the bow, excuse me. And there is the tip of the arrow, Al-Nasl. And from there, okay, we've been saying goodbye to summer recently when we stream. We have marched up from the Lagoon Nebula right there, M20 Trifid right above it, up through Scutum, M11, and M17 Omega, and all the cool stuff in this part of the sky right here. Up through Aquila the Eagle, there's Altair, the Eagle's Eye, and one of my favorites is a little star just above Altair. It's called Terra's Head. That's the top of the Eagle's head. And on up into Cygnus, Lyra. The Dumbbell Nebula we look at is right about here. and on up into Cygnus, where Satyr, the Gamma Cygni Nebula, is here. The Crescent Nebula is here, I believe. The Veil is on this side, if I remember correctly. The Veil Nebula.
Yes.
And then the North American Nebula is right there. And as we get a little later into the night, we're going to turn and look southeast. Here comes Saturn is now still in Aquarius. He's been in Aquarius for a year or two. And I'll advance the time a little bit. Saturn just went through opposition recently. Well, we'll give it a couple more hours, and hey, look, here comes Jupiter. He's up by before 10 o'clock now. Jupiter is in Aries, and we'll give it another hour or two. Okay, here comes Taurus, and we'll give it one more hour, 11:30 at night or so. There is Aldebaran, the Eye of the Bull. Here is the Hyades, the star cluster we mentioned. They think they have found one or several black holes in. And then just above Hyades is Pleiades, the Seven Sisters, also in Taurus. This is really cool part of the sky. And we've looked at the Crab Nebula before. The supernova remnant Mark mentioned earlier. The Crab Nebula sits right there next to, see these two stars here? Those are the tips of the horns of the bull. The Hyades are that V shape that makes the bull's head. And you project out to those two stars. Those are the tips of the bull's horns. And the Crab Nebula is right there next to that star, Zeta Tauri, I believe. And now Capella is up. Capella is sort of the winter companion to Arcturus. When Arcturus sets, Capella rises, and that sort of thing. And we get a little later, by midnight, 1 in the morning, well, Orion is coming up. I went out and looked the other night, and Orion is actually rising by midnight now at my location.
Wow.
So here comes Orion, and there's Betelgeuse, the other prime supernova candidate for our part of the galaxy. And the nebula is just there's the belt of Orion, and it's not quite up yet. And here comes Rigel. There's the belt, and there is the nebula. So you have to wait pretty late to see them still this time of year.
I prefer to, I prefer just to wait until they actually get up high enough in the sky to see. And I'm not going to wait until 2 or 3 in the morning to actually show this, right? I mean, we did that before. We've done that. And it's great to reach for the summer sky, because when you haven't seen it all year, it's like, I got to see it. So you want to show it right away, but sometimes you can't.
Yeah.
Practicality.
Well, okay. This is 1:14 in the morning. I like to say at local midnight, meaning take away daylight savings time. So it's really 12:14 at night, just after midnight. And Orion is up by then. And, it's getting closer. So if you're up at midnight, look east, you should be able to see Orion. And here comes Gemini behind. That's pretty much all I have, unless you wanted to dive even deeper to stuff.
Well, I was
going
going
to
to
go a little farther up in the northern sky.
Sure,
Perseus, Andromeda is well up. Cassiopeia. There's M31 and Andromeda right there.
That's the Andromeda Galaxy.
And I've said for the whole story of, I'm sorry?
Yeah, it's the Andromeda Galaxy. Yep.
Andromeda Galaxy, yes. Yes. The whole story of Perseus and Andromeda, the movie Clash of the Titans, that's all happening right here in this time of year. And believe it or not, here's Gemini. And before you know it, by November, Leo will be rising by midnight. And let's go ahead and fast forward here. 10, 11, here comes Leo. And the Leonid meteor shower will be happening. The radiant point is right about there. And that'll be November 17th. It's usually the peak night for the Leonids.
Yeah,
That's what you have to look forward to.
I remember seeing those one year, Daryl, and
so
and they were so amazing, and they tend to leave trains. That is to say, they create wisps up in the sky that you can see, and those wisps might be green. It's effectively the particles and the atoms in the upper atmosphere reacting with the energy of the meteor stream coming in, and you get like these little mini auroras created by the tails and trains of these meteors streaming into the atmosphere. So they look like little green trails left behind. It's really fascinating.
Yeah, when you see green in a meteor tail, that's usually oxygen, surprisingly. You can see other colors in the head of the meteor and all. The Leonids tend to be very colorful meteors. I was out, I think 1998, I was buying out a country road out in the far southeast corner of El Paso County where I live, way out of town. And Regulus rose right at midnight, and the meteors were already streaming out of the sickle of Leo, that's called, the backwards question mark. And it looked like Roman candles going off. And they were coming right out. Some of them came right at me, and it was really cool to watch. And they were all the colors of the rainbow. It was just tremendous. And this was actually a couple of years before the big meteor storm of 2000 or 2001, whatever it was. It was just a tremendous sight to see.
Yeah.
That's pretty much it.
Well, go back if you could. Let's go back to our current date. Because I wanted to highlight some of the objects you were talking about. Thank you. And thank you for that, by the way. That's fantastic. And your observations, of course, are always very welcome. But if you look at our current position, if you look at the Milky Way there, looking toward the center of our galaxy, as we move up from the horizon, we find all these fascinating things that we've seen many times before in Skyter Livestream. And one of them, as we mentioned, is the Lagoon Nebula, seen here. Okay, with and to the left of the lagoon, you see another nebula out there that's really, really pretty.
Yep.
And for the longest time, I never noticed it, and I think it was because I was just. Go ahead. You said something.
Go ahead.
Oh, okay. And that's the Chinese Dragon Nebula, so named because the squiggly line you see there kind of resembles a Chinese dragon, and I think the head of the dragon is the two little bright stars you see there, with the blue around them, and that little arc of red at the end of that sinuous thing.
The
That's
head of the dragon is actually at the other. The head of the dragon is actually to the other end of it, toward the right, toward the west.
Yeah,
but you do you see what you like.
No,
anyway,
that's true. I mean,
yeah.
But so anyway, so Lagoon Nebula and this are located in Sagittarius, and if you can bring that over, maybe show them. I don't know how easy it is to do that with, because you're using the online version of Stellarium, and
my pointer is right on the lagoon right now.
Okay, very good. Yeah, that's right. You can see that.
There is the Lagoon Nebula, and M20 Nebula is right there where my pointer is now. They're very close together.
Yeah.
M20 sits just above the lagoon.
And here's M20.
And then M24, M25. Let's see. There's one of my favorite globulars, Messier 22.
Okay.
And I'm looking for M17. I might have to type in to find it.
I do have a picture of it.
There's the Trifid M21 star cluster right next to it. I'm sorry.
I do have a photo of the Omega as well.
Say again, please.
I do have a photo of Messier 17, which is the Omega Nebula as well, which I'll put up.
All right. Roger that. Go ahead. Put it up.
So there it is. Okay, so you can see this is one of those regions again where hot stars, not necessarily all O stars, but some hot stars are actually causing the hydrogen gas to be ionized in this region. You'll notice above center, above the brightest part, you see the darkness, the dark stuff. That's not an absence of stars. That's actually the dark dust we've been talking about created by these large supergiant stars. They form this effectively ash in their outer atmospheres, made of carbon molecules, usually carbon molecules, and this stuff will float throughout interstellar space for millions upon years, sometimes a billion or more years, before they get swept up and go into being part of a new star that's being formed. And then when that star dies, it returns a lot of that stuff to the interstellar medium. So this is the Omega Nebula. Now, the interesting thing about the Omega Nebula is it's been thought that the Omega, as unlike the Lagoon, which is a stellar nursery where stars are still being formed, it's thought that maybe the Omega has finished its star forming, and so it's on the tail end and of star formation. So what that means is that this location in space with the Omega Nebula might be one of those where the hot stars that are ionizing the gas now, once they die away, might leave this area here with those black clouds of dark dust, of the fundamental foundational elements that create life, might leave this stuff for a future stellar body like a star, maybe the size of the sun and temperature of the sun, to form, which could lead to planets, which could lead to life. So again, this is the kind of location from whence life will come at some point in the future. Now, if we move north, Daryl, above this, and go into Cygnus, then we have other things that we've looked at up there, which are not quite at that position, but getting there. Okay. And when we go all the way up to Cygnus, and if you zoom in, let's do North America. Okay. If we look at this location, which is just above center where he's pointing it to now, okay, this is the North American Nebula. And it's called that because, as you see, it looks like North America within that green ellipse. And that dark area is the Gulf of Mexico in this nebula, so to speak. And that actually, in our telescope, Sky Tour, looks like this. So this is the Gulf of Mexico. And you'll notice that you have this beautiful dark nebula that is sitting in front of the brighter nebula behind it. Again, not a void of stars. It's a dark dust cloud, of which there's so much in the universe, and it's obscuring the nebula behind it. And then down near the bottom, you have this thing called the Cygnus Wall. It's an area where there are shock fronts from previous supernovae that have gone off and left this wall of material that's like a snow plowed into this position, and ionized hydrogen lights the way, ionized by stars that you can't even see because they're buried inside that black cloud up above that you see. A fascinating location.
And that dark cloud that makes the Gulf of Mexico in the North American Nebula, the bright star or stars that are lighting up the entire North America Nebula and the Pelican Nebula next door, the bright stars are hidden from our point of view because they're behind that dark cloud.
Yeah. Yep. And so this is another region. Again, in our Sky Tour telescope, this is just a 20-second exposure. And it's just beautiful. Now, just in this particular image above it, there is one more thing, and it's the other ellipse down below this current ellipse that Daryl's showing you here. All right. And that's called the Pelican Nebula. And the Pelican in our telescope, all right, there it is right there. All right. Kind of looks like a pelican lying on its back right now. Okay. But the Pelican in our telescope looks like this. Now, I think this is stunning, to be fair. This Again, an area of hyper intense ionization of hydrogen gas mixed with dark nebula, which are the black dust that we see in front of all this. Wispy clouds, gossamer streamers of black dust, which themselves are light years in width, interestingly. And I mean, this nebula is, oh gosh, I think the nebula's got to be what, 4,000, 5,000 light years away, if I recall.
I forget.
Or-
I don't think they're that far away. I forget.
It might be. I was wavering between 1,500 and 5,000 because it's either stars
was
or
I.
1,500. Yeah, okay. Well, anyway, either way, again, the stars doing the lighting up and causing the emission are not stars that we see with our eyes because they're buried, as Daryl mentioned earlier, and as I mentioned before that, deep inside these dark clouds. But fascinating locations. And then, but those are stellar nursery areas, areas where stars are being born. Now, Daryl mentioned Bach globules before. Bach globules are very important. There are areas where this dark dust will actually self-compact, gravitationally contract, and you'll get them isolating. Now, I had the pleasure of having classes with Bart Bach, the man who discovered these, and these Bach globules, which I always like to say in front of them, and these are Bach globules, right? Well, yes, they are. And the Bach globules represent the fundamental locations where new stars and now, as we know, planets are being formed. Really fascinating. Now, moving up from the North America, actually just moving back just a little bit, we have Satyr, which is the middle star in Cygnus, and that one is right there, and that nebula around it that you see is called the Gamma Cygni Nebula, and in our Skyter Live-Stream telescope, that looks like this, and that star at the top, that's Satyr. So as you can see, and again, this is just a 20-second exposure taken with our telescope. When we take people on tours, and Daryl's with us because he's another important part of this whole process. When Daryl joins us, we actually end up touring the night sky together. We show people things, and this is exactly the kind of thing that people want to see, and they want to hear about these black nebulae, these black dark nebulae. These dark nebulae are my hot button, okay, as an astronomer. I absolutely love these dark nebulae. They are very complex regions. There's not just carbon there. There's silicon, and there's many different forms of ices, from ammonia ices to formaldehyde to carbon dioxide ice to water ice, all that has congealed on these particles of dark molecules of carbon and silicon. So it's really an amazing genesis that these create. And once a star forms, that these ices might get sublimated, and now those are free atoms floating around in an early solar or stellar nebula for a new planet forming location. And that's kind of what I think is important to understand here. Now,
one more thing.
I do. Are we going to talk about the supernova? All right, the Eastern Veil right there.
Which supernova?
That one.
The veil seemed pretty obvious that you wanted to go to Cygnus. You've seen us do the veil before, folks, and just real quick here in Stellarium before we go to images. You've heard us talk about the Eastern Veil, the Witch's Broom, the Star 52 Cygni. Here is the Witch's Broom right here. This is the one I would say looks like a tornado. Here is Pickering's Triangle in the Central Veil. And here is that face we always see. It kind of reminds us of Alfred Hitchcock. There's the top of his head. There's his nose. There's his mouth. You see the face there. And maybe Mark can show you the pictures of it.
I do, actually. That's the Eastern Veil right there. And this is the Eastern Veil as imaged in our telescope. Okay. The Western Veil has that Witch's Broom that Daryl was talking about. I don't have that image in here right now, but I do have one of both the central and eastern veil, or western veil rather, and this is the eastern veil. Look at all that those gossamer tendrils. This stuff is the result of shock fronts from a supernova. Now, it has a gentle arc shape. That arc shape, if you can imagine completing the circle, that would kind of roughly point back to the location of the supernova that caused this. This is what we call a supernova remnant. And the supernova remnant is something that is really something that we'll notice is really a creator of a lot of the matter that we see in the universe. Now, in the time we have left, we can just talk about the fact that you see the colors there. Again, there are many elements represented in here, but they are dominated by the oxygen in the green and the hydrogen in the red. Okay. Undoubtedly, there's other ones that are represented. And a full spectrum of this supernova remnant would show that. Now, the lit up part, these are emitting light, right? This will show you emission of hydrogen alpha in the red and emission of oxygen 3, O3. Hydrogen alpha is the ionized hydrogen we talk about, and O3, that's Roman numeral 3, so it's OIII, is doubly ionized oxygen. And we'll see this in a lot of the supernova remnants, all right? But we'll also see it in the Wolf-Rayet stars. We'll also see it in the stars that die more quietly, like a star like our sun. It would also create a greenish nebula around it that would be oxygen 3 as well. So I think this is really fascinating to talk about. We will actually do more with Wolf-Rayet stars next time we talk as well, because we also have a bunch of examples to show on the Wolf-Rayet stars. I'm really excited to announce also that in our Arizona Desert Observatory, we've just changed our camera, and some of the images that you just saw, right, namely this one, and this one, and this one here, along with that one, okay, they look beautiful. These images represent images from our new camera. Our new camera has almost twice the resolution of the old one, and it's a smaller field. So we actually have twice as many pixels showing you the same stuff that a larger image showed with less pixels. All right. So we actually effectively have a much higher resolution system now that runs just as fast. So we're actually looking forward to it. And I'm going to be out there at the observatory this coming Tuesday. So in just 2 days, I'll be out there, and I'm going to be doing some adjustment work on the telescope to get it perfectly aligned, because as good as those images look, Daryl and I can see things that aren't right with it, and I'm going to go out and fix all that too. So we are looking forward to getting this telescope up and running. And status on the new telescope, we are closing in. We have a location for the new one, and the landowners have agreed to let us put an observatory on their property. And we're going to have, again, a fully green observatory. I like green. Green is better than, having to depend on a grid. And we're going to be able to show you things even better with even finer resolution. And we'll be doing it at the same time as using the other observatories. So we're going to have 2 images that you're going to see, a close-up and a wide field. So you're going to have both in one shot. And I'm just aching to do that. And
Mark, we are out of time.
Well, I saw the 3-minute mark and I tried to calculate, so I guess that's about right. So we'll talk more next week, guys. And I want to thank you for coming in, and we'll see you next week on Sky Tour Radio.
Good night, everybody.
Bye.